Thank you so much. And thanks for the organizers for making this event happen. It was very educational for me. Many talks were very educational for me, a little bit far away from what I'm doing on a daily basis. So that's nice. So I'll talk about, well, the beginning of the talk will be some material that's based on a paper from the end of the summer of last year. And then I'll move on to some work that's going to appear very soon and some work in progress. I'll try to be a little bit more pedagogical since I'm aware that most people in the audience are not working on these kind of things. Now, this field that I'm going to talk about involves in a pretty intricate way a lot of high-end modern mathematics. So there are many mathematicians here um, that made very important contributions that have direct physical ramifications. Um, on the other hand, there is also lots of physics papers here with names that many of you probably recognize. So it's a very nice field that intertwines between math and physics, and there's lots of development. So let me just introduce to the problem. And by the way, if there are any questions, please stop me at any point. If I'm saying something contentious or unclear, please stop me at any point. So of course, we've been used to the fact that symmetries are a cornerstone in the analysis of physical problems for over a century now. And one fundamental result is that of Nether, which is that if there is a continuous transformation of the action or the equations of motion or whatever that preserves the equations of motion or the action, then there is a corresponding conserved current and also a conserved charge that you can obtain by integrating the zeros component of the current or the charge density to get the charge. In quantum mechanics, this story has a little bit of a twist that has been also understood for over a century from Wigner, I believe. Probably it's less than a century, actually. So the idea is that symmetries are realized on the Hilbert space as unitary operators. And of course, as you well know, there is an exception for time reversal symmetry, which is realized as an anti-unitary. But let me not get into that. I won't discuss space-time symmetries in this talk anyway. So how does it work? In the context of some quantum field theory in d dimensions, this unitary operator is given by an integral over some d-1 dimensional surface. Very much like here, we integrate over a d-1 dimensional surface. We integrate the charge density. So in quantum mechanics, we get a unitary operator that secretly depends on some d-1 dimensional surface over which we've integrated the charge density. So for continuous symmetries, such as the U1 symmetry, we exponentiate the charge with an arbitrary coefficient, and we integrate over a d-1 dimensional surface. This star is just a shorthand notation for this integral. So I will often say that this surface is topological because, as you well know, charges are conserved, so you can deform the surface a little bit without changing the result. Now, when I say that this surface is topological, of course, it's an abuse of terminology. What I should really say is that there is a unitary operator that depends on the surface, but the dependence on the surface is only through the topological properties of the surface, namely which other surfaces it crosses or which other local operators it crosses. But okay, so this formalism, while not only discussed continuous symmetries, this formalism works exactly in the same fashion for discrete symmetries. So there we have some unitary that depends topologically on a codimension 1 topological surface. And when we want to say how the symmetry acts on the theory, we give a bunch of rules. So when we take the symmetry surface, we surround the local operator, we just get the usual action of quantum mechanics that the symmetry acts by conjugation. And we can even surround our local perturbations or our local operators with two surfaces, and then we get a group law. So the surfaces fuse, we call that fusion. They fuse according to the group law, and we say that the symmetry corresponds to some group law, since the space of transformations that leave the action invariant is some group. So likewise, the unitaries that we get in quantum mechanics form a group structure. And now there are lots of books, and this is textbook material of what you can do with symmetries. Sometimes you can gauge symmetries. Sometimes symmetries may have anomalies. Sometimes symmetries can be broken explicitly or spontaneously, and so on. Now, what I'm going to talk about is about various generalizations of the notion of symmetry. There's been a lot of work on that in recent years, both by the condensed matter community and by the high energy physics community. There's been a lot of progress on various directions in which symmetries can be generalized. So let me just quickly list, just as a quick review, of what kind of generalizations people have considered. So the first type of generalization that people have considered is when these unitary operators are not defined by integrating over a d-1 dimensional surface, but rather by integrating over a d-2 dimensional surface, for instance, or even d-3 dimensional surface if you are in higher dimensions. And these things are usually called higher symmetries. I will not discuss much this subject in this talk. Actually, it will only come up. It will only come up at some point, but it's not the subject of this talk. The other generalization that I will talk about is when these d-1 topological surfaces actually do not correspond to a group. So unlike the usual paradigm that Netter instilled into us that they form a certain group, I'll try to convince you that in fact that's not necessary. And there are many symmetries that don't come from transformations of the action. So they are in some sense beyond Netter's theorem. And they don't correspond to a group, but another mathematical structure that's called a fusion category. In fact, one can mix up the two notions. You can also consider d-1 to d-2 dimensional surfaces, which are non-invertible and so on. But I won't discuss that either very much here. Now, in condensed matter, oftentimes these symmetries are called categorical symmetries, meaning the symmetries which do not form a group. In high energy physics, we use sometimes the name non-invertible symmetries or non-symmetries or categorical symmetries. Mathematicians call it categorical symmetries or fusion symmetries. There are various names, but it's all the same thing. Are there any questions about the introduction? Okay.
Perhaps just what is a non-invertible surface?
That's why I'm going to explain now.
Yeah, okay, thank you.
So let me just emphasize, this is Carl, or I'm a miss. Okay, I'll explain now. So for every transformation of the action, because it comes from a transformation of the action, there is an inverse transformation. So in the Netter paradigm, for every surface sigma g, there is another surface that's called sigma g inverse. So that if you fuse them, you get the trivial surface, because g times g inverse is 1 in any group. However, it could in principle be that some surfaces are such that no other surface can fuse with them to 1. So they don't come from any group. There is no group that can give you such a thing. And therefore, they cannot come from transformations of the action. But they're still topological and conserved. Does that answer your question?
Yeah, kind of. Thank you. Thank you very much.
So they don't come from a group. Non-invertible is just one of their properties, meaning that there is no inverse. But there are many other properties. It's just that sometimes people call it non-invertible because one of the main properties is that there is no inverse. So let me now give you the simplest possible example of this phenomenon. So when we teach about symmetries, the first example we give is U1 or Z2 symmetry, whatever you like. So when we teach these categorical symmetries, that's the first non-trivial example actually. This is called the Ising category for obvious reasons. It resembles some things that you know from, like if you ever studied the Ising enyons, you have seen such formulas, but it's not actually related, at least not directly. So first you have a symmetry that's called U, and that's an ordinary Z2. It scores to 1. Obviously, it has an inverse. So if you take a U charge and another U charge, they fuse to 1. But then there is a more interesting symmetry that's called curly N in these slides. And actually, it satisfies a commutative law. N times U is the same as U times N, and it's the same as N. Okay, and that's also not terribly interesting. You could write down groups that have such multiplication rules. The most interesting thing is this. So if you take an N conservation law, and another n conservation law, they fuse to 1 plus u. So in particular, n does not have an inverse, and therefore this can never come from a group. There is no group from which you can get such a algebra of.
Zohar, can I ask a question here?
Yes.
Usually, what you have is multiplication law, which is, let's say, the would-be group law, but then you have addition in the last rule. So, what is this addition?
Oh, that's an excellent question. So imagine a correlation function. Imagine the correlation function that you put local operators, just a path integral, but then you also put surfaces. You're allowed to do that in the path integral. Do you agree?
Mm-hmm.
So when I say addition, what I mean is that the correlation function is just a word identity is equal to the correlation function with 1, so no surface, plus another correlation function where the surface is n.
Well, I know that because I know, in fact, where this comes from physically, but mathematically, what is it?
Mathematically, this is a fusion category. That's what mathematicians call this kind of structure.
So you have two operations then.
There are two operations. It's called the tensor. It's called the monoidal category. A monoidal category in mathematics has two operations.
Okay.
One is the space of morphisms is endowed with a linear structure, and the other is that you have a product.
Okay, good. Thanks.
But physically, physically, it's an overkill to use all these scary words. Physically, you just have identities that you can use in correlation functions.
Sorry, could you perhaps give a real example? I mean, not an example.
That's going to be real. I'm going to give you lots of real examples. I'm just saying that this is the simplest mathematical structure that we can realize in interesting quantum field theories or many-body systems. Okay. There are lots of examples. People have written lattice Hamiltonians with this structure. People have written quantum field theories. Yeah. I want to just make one comment for maybe more advanced listeners that this is commutative because of that, but in general, the fusion rules don't have to be commutative. And there's some story about that I don't want to get into about braiding. Okay, that's what I basically said before. This is an identity we can use in correlation functions. And now also I wanted to respond to the question of what do I mean by it being non-invertible. So there could be a local operator sigma, so that if you surround the sigma with n, you get 0. This is impossible with ordinary symmetries. Why? Because with ordinary symmetries, we get an adjoint action. And an adjoint action cannot take an operator to 0. But with these things, it's possible that some local operators are actually annihilated. And that's why this is non-invertible. You cannot invert this operation. So you cannot put anything outside that would make it non-zero all of a sudden. And then there are word identities of what happens when you take local operators and pass them through these topological lines. You get defect operators, junctions of topological operators. There is a big story here of the various word identities that you can get from these things. Okay, so let me give you an example. So the simplest theory that I know of that has this symmetry is the Ising model at the critical point. So the one-dimensional Ising model, 1 plus 1 dimensional Ising model, when you tune the temperature to the Curie temperature. So you take the 2D statistical system, if you like, you tune the Curie temperature to the temperature to the Curie temperature, these symmetries emerge, and they can be even constructed on the lattice. Or you can think about it as a quantum system at 0 temperature, where you just tune to quantum criticality. That's the simplest, by far the simplest model that has this symmetry. If you go away from criticality, the symmetry is broken. Actually, this conservation law ceases to exist. So in fact, it's not just a symmetry of the Ising model at criticality. There is a lot of literature on deformations of the Ising model. And some of the deformations, in particular, the so-called TT bar deformation of the Ising model, preserves this full symmetry. This could also be a symmetry of models that are gapped. Hamiltonians which are gapped also can admit such symmetries. And I'll give you an example now. Just to quickly review, what is a gapped Hamiltonian in 1 plus 1 dimensions? A gapped Hamiltonian is just a bunch of states which have 0 energy. Well, in one dimension, we can take the space-like manifold to be just S1, and just we have a bunch of states on S1. That's what we call the gapped gapped Hamiltonian. And there is a very non-trivial theorem that these symmetries, the non-invertible symmetries, must act on these ground states in some non-trivial way via matrices with integer coefficients. And that's the key point. NIMREP stands for non-negative integer matrices. So there is a theorem that you must realize the symmetries on the ground states in some very particular way. And that's one of the reasons that people are so interested in these non-invertible symmetries, because due to these facts, once you know that you have a Hamiltonian with such a symmetry, you can immediately prove a Lipschutz-Matisse type theorem, that there cannot be a unique ground state. Or in particle physics language, you can immediately prove that the ground state is the the ground state must be degenerate. If it's gapped, it must be degenerate. So you can immediately prove of a strong result.
Sorry, is it because there are no trivial representations for this algebra?
There is no one-dimensional representation for this algebra. That's how you would say it mathematically. That this algebra doesn't have legal one-dimensional representations. In fact, it doesn't even have legal two-dimensional representations. So if somebody handed you a Hamiltonian in the ultraviolet, a weakly coupled system with some spin-spin interactions, and you found such a symmetry, you would immediately conclude that if it's gapped, it has to have at least 3 ground states. And that's the simplest representation of this algebra. Okay? So this is the matrix U. Sorry, it should be curly U. I forgot. And curly N. This is the simplest legal representation of this algebra. So the conclusion is that these symmetries can be realized on gapless systems, or they can be realized on gap systems, but then you have to have at least 3 vacua. Are there any questions?
I guess another option would be the symmetry to be spontaneously broken also, right?
Well, that's what it means for it to be realized on 3 vacua.
Oh, I see. But what about, so that means that it always has to be spontaneously broken?
No, it could be gapless. Like in the critical Ising model example, it could act on the massless excitation of a CFT in 2 dimensions. I gave you here just a hint of how it acts on various local operators in the Ising model. You might recognize the defect operator, the spin operator. I didn't even draw the energy operator, but it acts actually on the energy operator too. So the conclusion is that it can be realized either on degenerate gapped ground states or on gapless systems. And there are by now tons of theories in 2 dimensions which admit to these funny things that are non-Noether symmetries. Let me just say a few more words about the foundations of the subject. So the first thing you have to determine is the rules of how you multiply the symmetries. This is called fusion. This is what I gave you here. This is the fusion for the Ising case. Then you have to determine the action on local operators. This is typically very difficult, but it can be done. And this is what I gave you an example here of how it acts on the spin operator in the Ising model. And finally, you have to try to understand which representations are allowed. This is a question just in representation theory. You must find legal representations of this funny thing. This is called in mathematics NIMREPs, because I told you that these representations have to be with matrices with integer coefficients. And there is a huge industry in mathematics trying to classify these representations. Those of you who are interested in this, I very much advise you to take a look at the talk by Terry Gannon, who is basically a mathematician working on that. He summarized all that's known about the representations of this fusion categories in a recent talk. Now, let me get to the point of the talk. So I gave you examples of gap theories and I told you that in principle, it can act on gap theories or gapless theories. But the reason that I'm giving this talk is that we found a very cool application in actually gauge theory dynamics. And I'm going to tell you, just summarize quickly what we were able to do with the symmetries as far as shedding light on some gauge theory goes. So there is a very famous problem in particle physics, which is to understand gauge fields coupled to various matter fields. This also appears in condensed matter when you study deconfined criticality, for instance. So here we're talking about 1 + 1 dimensions. We have an adjoint fermion psi and a gauge field in the SUN. an SUN gauge field. Sorry that I forgot to write it in the slide. So we have an SUN gauge field in 1+1 dimensions coupled to a single Majorana adjoint non-chiral adjoint fermion. This model is strongly coupled. It probably confines, and the reason that people are so interested in it, and there are many, many papers on this model, is because it's two-dimensional and it probably exhibits phenomena that are similar to four-dimensional confining theories. So let me now quickly tell you what's known about this model. First of all, this model doesn't have that many symmetries because this fermion is in a real representation. It's a single Majorana fermion. There is basically just one chiral symmetry, which is Z2, and it only appears at 0 mass, and that's it. So the model with the non-zero mass has just charge conjugation symmetry and fermion number symmetry, and that's it. So this model has very, very few symmetries. And most of what we know about this model comes from conjectures or lattice simulations or semi-classical expansions. So I'm not going to talk much about the dynamics of the model at finite M. This is actually easier than 0M, but I don't have time to review everything. It's too short of a talk. So I'll talk about this massless case. In the massless case, there is an axial symmetry. In addition, because this model doesn't have propagating excitations in the fundamental representation of the group, there is a certain conservation rule for strings. So this is called the one-form symmetry. So if you take a string for a fundamental probe quark, it cannot be broken by adjoint fermions. Now, let me just quickly review the literature. There is a very nice and deep observation just from last year, actually, or a year and a half ago, by this group, which says the following: that if you act with this Z2 axial symmetry on the vacuum, you create a string with n over 2 units of flux, where this applies only for even n. So what people have been able to prove using ordinary symmetries, ordinary Noether symmetries, is that if you put into the system, if you put into the system probe quarks in a representation with anality n over 2, they are deconfined. So that means that there is no linear force, no linear potential trapping them into a bound state. And that was proven rigorously using the symmetries of the system that are standard symmetries. For the case of SU2 gauge theory, this actually leads to complete deconfinement because the n over 2 representation is the fundamental representation. And there is a sequence of papers by David Gross, Igor Klebanov, who also spoke at this conference, Matitz and Smilga and Hashimoto about this model, where this agrees perfectly with what they said. And actually, you cannot say much more using ordinary symmetries. But now I'll tell you something surprising that has to do with categorical symmetries, or sometimes they are also called defect symmetries, actually. So I'm running out of time, so I'll jump quickly to the conclusion. It turns out that this SUN gauge theory has a huge number of non-invertible symmetries. So there is a huge fusion category with an exponential number of conservation laws. This is completely, if you just look at the Lagrangian, there is no way to see it. It's hidden. But we were able to prove that there is an exponential number of conservation laws that are invisible, and they only apply at 0 mass. And of course, once you have such a huge number of conservation laws, the model becomes very constrained. So the hope is that, since if you realize that there is such a huge number of conservation laws or hidden symmetries, you might say something more dramatic about this model. And indeed, this is possible. I have a bunch of technical slides here about category theory that I'm skipping since I have only 5 minutes left, I think. I'll just slide quickly to the bottom line so that you can maybe just get a sense of what you can derive, and that's it. So the first thing that we were able to derive from these symmetries is that in fact all the representations are deconfined, not just the n over 2 representation, but the model is completely deconfined at 0 mass. This is surprising because there is only an adjoint fermion, and it turns out that you can screen the confining force between fundamental quarks using just a dynamical adjoint fermion. But that's only true when the fermion is massless, when the adjoint fermion is massless. And there is a very nice semi-classical picture of fractionalization of the charge that leads to this deconfinement that we explained in the paper. The second thing is you can ask how many ground states does the system have? There is a huge fusion category with exponentially, as I said, exponentially many generators or conservation laws. So you have to try to classify which kind of ground states could appear. And it turns out that the number of ground states is also exponentially large in N. This is also a little strange because it means that if you take the N going to infinity limit, there is a Hagedorn transition at 0 temperature. There is just like, strictly speaking, infinitely many vacua. And as soon as you turn any non-zero temperature, the thermal ensemble doesn't make sense if you take N to infinity first. Okay, so there is a huge number of ground states, a huge number of conservation laws, and complete deconfinement. That's what we found so far. But there is something more that you can do. You can ask about the tension, what you can ask about, okay, so this is about the massless theory, but what if the mass is non-zero, but very small? Now, in particle physics, there is a very well-established way of thinking about such problems. We start from the massless theory, we understand it, and then the mass is a small perturbation. That's what we do in chiral perturbation theory in pion physics. And you can do the same with these funny non-invertible symmetries. As soon as you've understood in so much detail the massless theory, you can turn on a small mass. Even though these non-invertible symmetries are broken, you can still use them as softly broken symmetries. And doing that, we've found an exact formula to leading order in M/G for the tension of K strings. So here, the idea is that you put a representation with K boxes, and you ask what is the force between these probe quarks. And that gives an exact prediction. In fact, such formulas appeared in some literature on integrability, but we don't know what is the connection. This leads to this formula actually means that there are confining K strings, and one can try to match it to particle physics data about the tension of K strings. There is also some story about the fact that as you change the mass, the force between K strings seems to change in a qualitative way, and that would be something that would be great to understand. I'll just end with a small remark that it's a little surprising that you can obtain exact predictions without supersymmetry or holographic duality or large N. But this is the power of these non-invertible symmetries, I believe. Now, I have just 7-8 more minutes. I'll make one last remark about this model. So this model admits 4 Fermi interactions. And in fact, if you were to construct this model on the lattice in a condensed matter fashion, like in a condensed matter way of thinking about it, you would probably induce some 4 Fermi interactions. So to get a complete picture, it's important to consider what's the effect of these 4 Fermi interactions. Now, using the non-invertible symmetries or the categorical symmetries, we proved that this 4 Fermi interaction doesn't do anything whatsoever. So every single thing that I've said in this talk remains exactly true, even when you add this operator to the Hamiltonian. This operator is a little more interesting. And using the defect or categorical symmetries, you can also analyze it completely. And what we found is that it leads to confinement of all the representations except for the N/2 representation. This agrees with this scenario in the paper of Sherman et al. However, depending on the coefficient of this operator, we also found some other exotic phases where some strings become of negative tension, and we don't understand it at the moment. Perhaps putting a negative coefficient in front of this operator is not allowed, but we don't understand this at the moment. Finally, you can ask, is there a lattice construction of this model that would actually have these non-invertible symmetries? And I think the answer is yes. Recently, condensed matter people have written lattice models with fusion symmetries or categorical symmetries. So there is no fundamental obstacle. Okay, so regarding this O2 operator, which changes the dynamics of the theory a little bit, I just wanted to say that before we started working on that, people have found that this operator is not generated in perturbation theory. So if for some reason it's 0 in the UV, the Wilsonian RG flow doesn't generate it. This looked very puzzling, but it's explained very nicely by the non-invertible symmetries. The word identities of non-invertible symmetries prohibit this operator, even though it's allowed by all the ordinary symmetries. Now, there is a principle of naturalness that 't Hooft suggested in the 70s, which is that if an operator is allowed, it should be generated, if it's allowed by all the usual symmetries. But here we see a counterexample. This operator is allowed by all the ordinary symmetries, but it's not generated. And the reason is that it's protected by the categorical symmetries. I'll conclude. So basically, I try to quickly convince you in this very short talk that the notion of symmetries should be extended to include this more complicated objects, categorical symmetries, or non-invertible symmetries. And they actually are very similar to all the symmetries that you know, and they have the same, they obey very similar rules. They can be spontaneously broken, they can be gauged, they can have anomalies, they lead to word identities, and they can even be softly broken, as I told you with the problem with the string tension. I showed you some applications in 1+1 dimensions. Many things that I said are just predictions for this gauge theory. It was not tested yet on the lattice. So it would be nice to test it. And of course, there are many more examples you can study with these tools. So that's it. Thank you.
Thank you, Zohar, for this nice. I found it quite pedagogical, and also for self-chairing your your talk. That was great. And I think we already have a question from Alex. Please.
Yeah, thanks for the talk. It was very illuminating. In your last example, N, I missed it. N was the number of flavors, right, of your Majoranas? I mean, capital N.
Okay. Yeah, it was very fast. I can't explain.
No, it's okay.
I mean, SUN was the group,
yes.
and the number of fermions in the adjoint representation was 1.
Ah.
So there is one fermion in the adjoint representation, and the gauge group is SUN. I actually spent probably a month of my life trying to generalize this story to 2 Majorana fermions. I have a good reason for that. Like Subir and Igor have a very nice paper for condensed matter applications of the case of N f equals 2.
Yeah.
Yeah, you could repeat a lot of the same things. You could predict the confinement. You could compute even some transport coefficients. Yeah. But I was not able to compute the string tensions, and that's why I was not able to generalize this particular formula yet.
The actual question would have been, I mean, maybe that makes sense only for more than one flavor. I mean, in principle, you could bosonize the fermion action to arrive at some, I guess, some ON Vesomino model. And in that language, any intuition of how we should think about your non-invertible symmetries?
Yeah, I had a few slides about that.
Oh.
I jumped over many slides.
I see.
So even with just one Majorana fermion, you can formally bosonize it to spin n squared minus 1 level 1 Wassermann-Witten model.
Yeah.
Now, this model, now you have also a kinetic term for the gauge field. So this is a gauged way. Now we have to gauge SUN, right? We bosonize the fermion, then we need to gauge SUN level n.
Mm-hmm.
So we're talking about some Wassermann-Witten model which is gauged, and it's still strongly coupled. You still cannot solve it.
Yeah.
But still, this presentation of the same theory is useful. Why is it useful? It makes it a little bit easier to understand the non-invertible symmetries, because the spin n squared level minus 1 level 1 theory has Verlinde lines, and the Verlinde lines are by definition invariant under the Lie algebra of spin n squared minus 1. But here we want to solve a different problem. We want to understand the non-invertible symmetries of this model that are invariant under SUN level n. So what we had to do, we had to solve a problem that's similar to what Verlinde did, but it's not the same. And this leads to lots of complication in category theory, solving this particular problem. But still, the bosonized presentation is the way to do it. Mm-hmm. So the special cases of spin 3 and spin 8 can be done right away. We can understand all the fusion symmetries using the Verlinde lines. But as soon as you go to spin n squared minus 1 for n bigger than 3, you cannot use Verlinde's technology anymore. And that's where we needed to use much like cutting edge mathematics from Etinghoff and Ostrich and Kirillov. They invented something that's called alpha induction that basically allowed us to understand the non-invertible symmetries of the system.
Okay,
So
okay.
this really forces you to use some cutting edge mathematics, starting from SU4 gauge theory.
Okay, I think we have another question from Hugh. I apologize if I don't pronounce.
No, it's okay. Perhaps a mathematical question. I guess the notion of irreducible representation extends to these fusion algebras. Are the number of such representations typically finite or infinite? Did you hear me?
Yes, I heard. I even recognize your voice. It must be Hugh, right?
Yeah.
Yeah,
Yes.
I started thinking about your question. That's why it's finite. The number of irreducible representations should be typically finite.
So that restricts the number of physical possibilities.
Yeah, but you're allowed to do irreducible. You're allowed to. It's allowed that the space of vacuum would be an irreducible representation.
Sure. But I mean, if there's more than, there are several irreducible representations, there are more possibilities, aren't there?
Yes. I'll make sure that what I told you is always correct, and I'll send you an email if I said something wrong. But I think that the space of modules, these representations are called modules. I think the space of modules of fusion categories is in one-to-one correspondence with the representations of Hopf algebras. So I think it's finite. But I'll make sure. I'm writing down to myself to make sure that this is always correct.
Okay, well, thank you.
Yeah, could I just make a comment? Hi, Zohar. Thanks for a nice talk about these quartic operators. I mean, we used to think they're not generated because without them, the theory is basically super normalizable or even finite in some sense. But once you add them, you clearly get logarithmic divergences in the UVs. So there was a kind of that argument that it's two different theories. One has RG flow, the other one basically doesn't.
Yes, Igor, what I meant to say, I said it again very fast and a little imprecisely. Suppose you add this operator to the action. Let's call this coupling G. And let's call the coupling of O2 G prime. Now, people have computed the beta functions of G and G prime. And what they found is that if G prime is 0, it remains 0. This cannot be explained because the coupling G preserves all the symmetries and it could generate O2. You could say that maybe at large n, O2 is double trace, maybe there is some, but let's say finite n equals 3, n equals 2, or n equals 5. O2 is not generated. And people have done this computation to 1 loop, 2 loop, and my student even managed to prove it to all orders just by Feynman diagrams. And this cannot be explained with symmetries, I believe. There is no symmetry that can explain that because both O1 and O2 are invariant under the Fermi number, are invariant under charge conjugation, and are also invariant under the axial Z2.
Right. Particularly referring to the case where you start with both G's being 0 and just having gauge interaction.
Of course, then it's not generated because the model is super normalizable.
Right.
But and let's say that we turn on O1. O1 doesn't do anything. O1 doesn't do anything in the dynamics of the model, as I said. So you can turn on O1 and O2 is not generated. And I believe this is a striking violation of naturalness because O2 is not generated, but there is no reason our symmetries go. But I think that we gave an explanation that O2 is non-invariant fusion symmetries.
Okay, thank you.
I think Elias has a question. Yes.
Zohar, one more question. In the model you studied, of course, you used the bosonization, etc., and eventually you mapped the problem to a CFT that was topological in the infrared. And I guess this is the way to see what the symmetries in the fusion algebra is. Now the question is that in general possible? That is, do you have to go through a CFT to see that type of symmetry? And a related question is, do we know any such symmetries beyond 2 dimensions where we don't know how this fusion emerges, at least from something else than a 2D CFT?
Right. So let me first answer the second question. There is an example in higher dimensions that many people are looking at now, where this phenomenon happens. It's called Alice electrodynamics. Are you familiar with Alice electrodynamics?
No.
It's like Alice in Wonderland, that the gauge group is O2 rather than SO2.
Mm-hmm.
So there is lots of papers from recent couple of months about a non-invertible symmetries in Alice electrodynamics. I can send you references if you want. Send me just an email.
Okay, please.
So there is a story in 3 and 4 dimensions actually, and it realizes a fusion category that's a little different from what I explained here. Okay, now for the first question, I actually didn't go to a CFT. The proof that there is 4 to the n conservation laws is a weakly coupled computation in the ultraviolet, far from the infrared. The proof that there are many symmetries is something that you establish in the ultraviolet, and then you just study the consequences.
So you mean these are the symmetries of the free fermionic theory?
No, these are the symmetries of the free fermions with the tiny gauging, tiny but non-zero gauging. If you just had free fermions, there would be far more symmetries because it's a free field theory and there are lots of symmetries in free field theory. But once you weakly gauge the SUN subgroup, the number of symmetries is reduced and you compute the symmetries at that point. So we computed the symmetries for small non-zero G and then just proved that it doesn't change under the renormalization group flow.
And how do these symmetries act on the free fermions or the almost free fermions?
That's a question that is impossible to answer because you can only say how it acts on well-defined local operators, namely gauge invariant ones. So we have a whole section. We have a whole section in the paper that computes how they act on the bilinear. Perhaps it's the simplest gauge invariant operator. So we have a whole section that we give you for n equals 2, 3, 4, 5, 6. We explain how it acts on the bilinear.
I see. And I presume this is the same, of course, algebra that appears in the infrared topological, let's say, Coset model, right?
Yes.
Now, do we know other examples of fusion algebras in 2 dimensions that do not reduce to some Verlinde algebra?
Yes, this is not a Verlinde algebra. This algebra that we have in this model is not commutative. Verlinde algebras are always.
Oh, I see.
This is not a
I see.
Verlinde. As I said, for n equals 2 and 3, it is a Verlinde algebra because of some accidents that are written here. But starting from n bigger than 3, you need to use something else, and you don't get the Verlinde algebra.
I see. Thank you.